Hi everyone, welcome to this A-level physics paper walkthrough. We're going to go through AQA paper 1 today from 2024. So use the timestamps at the bottom to find a question in particular, or just watch our way through and learn how to answer a full paper for A-level physics. So we'll start off with the first question down here, which is asking us to name the 4 fundamental interactions, basically the same thing as the 4 fundamental forces. And it's only 1 mark for all 4, so we've got to get them all correct. So the 4 are gravity, and then we've got weak nuclear, and we've got strong nuclear, and then the final one is going to be electromagnetic, which is the name of all 4. You actually don't need to say nuclear for this particular mark scheme, although you could be asked to specify which one it is in the other ones. Next is the products of a decay of a free neutron. So in a free neutron, we should know the decay equation is basically what happens in beta decay. So we have turns into a proton plus an electron plus an antineutrino. So for the products, we just need to list the right-hand side of the equation. So we'd say proton, a beta minus particle. You could say an electron here as well. And then an antineutrino would be the third thing. Again, all 3 got to be correct for 1 mark here. Next is which of the fundamental interactions, these ones up here, is responsible for that decay, is the weak nuclear interaction. And the reason we know that, well, it's really one of 2 options, right? It's either weak nuclear or strong nuclear force. This weak nuclear, I don't know why I spelled that twice there, because it contains, or the interaction involves leptons. So if it involves leptons, it can't be the strong force. It has to be the weak nuclear force. Or you could say there's a change in quark or something similar to that. So you could say a proton to a neutron, there's a down to up quark change would also be absolutely fine for the second mark here. Next, we've got the forces between 2 moving electrons cause their paths to change. Explain using the concept of exchange particles. Why is it the electron paths change? This is quite an interesting question. It's 3 marks, and it seems like a particle physics question. We have got to talk about momentum here as well when we talk about exchange particles. So just a quick sort of recap. If we have 2 electrons, if I just draw out the little Feynman diagram here, you don't need to draw this out. But basically, if they come close together, they're going to obviously repel each other. They do that by exchanging a virtual photon, which means that they sort of repel each other and they move further away from each other. Like that. If we were describing this in words, we need to be really clear about what the exchange particle is, which is the photon. So you get a mark for mentioning that somewhere in our answer, and then for saying that that exchange particle, the reason it's able to exert a force is because it has momentum. So we'd say something like the electron it exerts a force by emitting, or by an exchange particle. And here that is the photon. And then we say something like the photon has momentum. So in this diagram here, if the photon, it says, go in this direction, due to conservation of momentum, this electron has to recoil a bit this direction, and this electron will receive the momentum from the photon and will go in this direction. So basically, say photon has momentum, so therefore the 1 electron has momentum backwards and the other forwards to conserve momentum. Now for this third mark, I'm not sure how other ways you could really say it. You have to talk about momentum for this mark to apply. There's not many other ways of saying it. The easy mark here is to talk about the photon is and the fact it has momentum, and then for saying the momentum is conserved when 1 exchange particle is going between 1 electron and another. Let's move on to question 2 then. So question 2 on this side of the page, we've got a positive pion collided with a neutron. And in the interaction, we have a positive kaon produced along with this particle here, which is a sigma particle, which you're not expected to know for A-level physics, but you can be asked to sort of determine what's in it just from the information they give you. So here they tell us, really important piece of information, it's neutral, obviously by the 0, and has a strangeness of -1. And the interaction can be used to deduce the classifications of this particle here. So because it's an interaction, we know it's observed. That means that the conservation laws apply. So in conservation laws, that means we're talking about charge being conserved, we're talking about baryon number being conserved, lepton number being conserved, and also strangeness being conserved as well, potentially if it's a strong interaction, which we don't necessarily know about yet. So basically, we should know for these three particles what they are. K plus, I'd recommend memorizing. You don't have to know that necessarily, but it was a good idea to figure it out. And then we'll figure this one out once we've done the other ones. So we should know a positive pion. It's not a baryon, but it is a hadron. It's a hadron and it's a type of meson. A neutron is a baryon and it's also a hadron. A positive kaon is a meson and also a hadron. And then this particle down here, if we look at what we've got on the left-hand side, the right-hand side, we've got a meson and a baryon. Must make a meson and also must be a baryon as well, because otherwise baryon number is not conserved. We've got +1 baryon here. We must have a +1 on this side as well. So that's how we can figure out our superparticle is also a baryon. Down below it says a conservation rule predicts that the following interaction, so it's a slightly different one to this one, will not occur. State the conservation rule. So let's look at those four we just mentioned and let's see which one it might be. So if we look at charge, so you don't have to do this in your answer line, you can do it anywhere really. But charge, I've got -1 for the negative pion, +0 makes -1 plus 0, so that's fine. Baryon, we just said that the baryons are the neutron and the sigma particle, so that's fine. Lepton number, there are no leptons involved here, so basically 0 makes 0. So it has to be this last one, which is all about strangeness. So the one that can't occur is if we look at our initial particles, I've got 0 strange quarks, 0 strangeness in our pion and in a neutron. And in our negative kaon, the way you know about kaons is that they have to have strange particles or anti-strange particles in them. So if it's a negative kaon, that would therefore mean it's got to have a negative charge overall. So that means it's a strange, and it's then going to be an anti-up particle, because that would mean that's got a charge of -2/3, and also a strange quark has a charge of -1/3. Those are all in your equation sheets. So therefore, it means it's negative. So if it's got a strange quark in it, that means it has a strangeness of -1 in our positive kaon. For the other particle, we're told it has a strangeness of -1, so that's where that information comes from. So actually, this is the one we've got a problem with, because we've got -1 strangeness in our negative kaon, and we've also got -1 strangeness in our main particle, and obviously -2 doesn't add up to 0. So we put it in words something like this, is that conservation will state it, we get a mark for saying its strangeness is not conserved, and then we've got to go about proving it. So basically we'd say essentially what I've just been drawn out here. So we'd say K minus and sigma minus have strangeness is equal to -1. So therefore we'd have the left-hand side, I'm going to write LHS here, you can write left-hand side, strangeness, we just said earlier, is equal to 0. On the right-hand side of the equation, the strangeness is equal to -2. So therefore, we've already said it, but it's not conserved for this particular interaction. For all conservation rules questions, you do need to be that specific with writing out the numbers. Don't just assume the examiner knows what you're talking about. Be really, really clear with what you write. Next up in this question, we're talking about rest energies. Now, with the rest energy question, the formula sheet, the data sheet is your friend, because you have given to you all the rest energies of any particles basically that could come up. So in this one, we're talking about a pion and electron, a positron and a photon. Those are all here. So don't feel like I can't do this question. It's just about looking in the data sheet and then interpreting that information. So I'm going to leave this on the side here while we answer this one. This question asks us to compare the rest energies of the particles involved in this new decay. So this is a neutral pion. What I'm going to do is just write down what they are from the equation sheet, and then basically it says to compare them. So basically what is there before and what is there after, how do they compare? So we'd say the rest energy of our neutral pion is equal to, in the equation sheet, we've got 134.972, and the rest energy of our electron plus our positron, they're going to have the same rest energy because they're antiparticles of each other. They're going to have the same. That's why it's got the plus or minus sign there. So it's going to be equal to 2 lots of 0.510999, which is going to be then equal to double that, and that's 1.021998. I should put mega electron volts at the end of these, shouldn't I? And the last one is the rest energy of the photon is equal to 0. So even though it might be a really obvious thing to write in your answer sheet, just write obvious things. It says it up here, so let's just put it in. So then if we compare the rest energies of the particles involved, we've got the pion up here, it's got 134, 135 mega electron volts. Down here, both of these products together have much, much, much less of a rest energies than previously. So we'd say a little statement like this. So we'd say, therefore, the rest energy of the product, so you could say the pion here is much bigger than the decay product. So what's on the right hand side? Next one we say is a decay of a neutral pion leads to production of further gamma photons. Explain why. What they're trying to get at here is the idea that in this decay we've got a positron and an electron. A positron and electron, matter and antimatter meet, there's going to be annihilation occurs. So the answer for this question is when those two particles meet, we know two matter particles meet, they're going to turn into energy in the form of photons. So that's where the photons come from in annihilation and be specifically your answer, annihilation of the electron and the positron together. Next question is quite a common one. It seems like one that is hard to prepare for, but it comes up a lot. It is in your specification. It says the Standard Model is a theory that classifies elementary particles. Evidence has been collected. However, Standard Model has only been used since this year here. Why is progress in particle physics slow? Now, the versions of this question could be, why is it hard to make progress? Why does it take time? Why does it take money? All those kind of things. The answer, there's lots of different ways of saying it, but in terms of the progress, basically, there's either because it's got expensive equipment or hardware infrastructure, or you could say you need, sort of engineers to kind of collaborate with physicists, and you lots of physicists analyze data, things like that. Okay, so we'd say something like equipment needed for research. So we're talking about things like a Large Hadron Collider here, I should say, very expensive. Okay, lots of options in the mark schemes here. Don't say things like, don't be vague. Okay, so that would be one thing to talk about. Not just it's expensive, but the equipment you need to do it is expensive. That question's out of 9. Let's move on to question 3. So question 3 is all about waves, and we've first of all got prisms. Bit of an unusual setup here. Got a triangular prism with another sort of prism right next to it. Our first task is to complete the ray or the path of the ray inside the block. So it should be obvious that initially it's going in, if I was to draw a quick normal on here, as it's going from air into a block, it's going to have a higher refractive index inside, so it's going to bend towards the normal. However, this question, you've kind of got to go in reverse because we know here it comes out at 90 degrees. We then know it's got to enter that boundary at 90 along the normal as well. So if it's going in along the normal, then basically I know exactly how this is going to bend. It's going to bend exactly in this way to mean it goes straight along the normal, going from B into the interface the interface between B and the air. So it looks something like that. We're asked to deduce which prism has the greater refractive index. So bear in mind, refractive index meaning how optically dense the material is. So to understand this, we've got to, again, draw a normal on. This time we're drawing a normal here. I'm a bit more careful with this time because this is the one where it's our answer sort of depends on this. So the normal where it meets the boundary here, let's look at these two angles. Now you can get a protractor out and measure them. However, hopefully it's obvious that this one, the angle of incidence here, is a bit bigger than the angle of refraction. So what does that mean? Well, let's compare. If the angle of incidence, if it's going from, let's say, air to glass, we know that the angle of incidence will be bigger than the angle of refraction. So therefore, B has a greater refractive index. So if you wanted further proof of that, you could rearrange Snell's law, do refractive index material 1 times our side of the angle material 1 equals the same thing for material 2, and sort of do ratios of that if you wanted to. However, generally speaking, we know we've got to go from a lower to higher refractive index. You can always just consider the example of air. So air's got to be lower to higher because the angle gets a lot smaller. So it's therefore going to be the refractive index of material B is bigger than that of A. And we'd say because the angle at the boundary, the angle of refraction is less than the angle of incidence. And again, you could use Snell's law to back yourself up here, but that's all the mark scheme's after for this question. Next, we've got just a recall question. So the block is often used with telescope to investigate stars. It can be used instead with a refraction grating. Describe one non-astronomical application of a diffraction grating. So basically means something not to do with space. So there's a few different ones the mark scheme would allow here. Probably the easiest one, the one you might come across most commonly, is with diffraction gratings, basically in chemistry, essentially. So to use the wavelength to analyze, like the mark scheme says, chemical composition, basically what's in a sample. Um, of a sample. So the idea is basically if you shine the light through a sample, the amount it diffracts will tell you what's in it. You could also say things like entertainment shows, so light shows, disco, all that kind of stuff. You could actually say to analyze the chemical composition of the sun, which I guess is not technically astronomical, but I'd argue potentially it could be considered to. But that would be absolutely fine for the 1 mark here. For the next question, we've got a slightly unusual looking graph where basically a spectrum of light. So if you can imagine it, this is the whole, colors of light going from about 300 to 700 nanometers. There are 2 lines in the spectrum which are labeled. The light passes at a normal instance through a diffraction grating. We're trying to find the number of lines per meter, and they label it G just to confuse people instead of capital N, for example. The first order diffraction angle, it says, is 28.2 to the normal. This is of X. Then it's asked to calculate G. So hopefully it's obviously a diffraction grating. There's only one real equation we use with it, which is the n number of orders times by the wavelength is equal to d times by sine theta. Now in this equation, n is number of orders, that's just 1. Obviously theta is the angle. D is going to be equal to the grating spacing, so the gaps between each grating. Now the grating spacing, usually you need to find it by doing 1 divided by the number of lines per meter. Now, in this case, we're trying to find the number of lines per meter. So if we find D, we can then do 1 over it to find what G is, number of lines per meter. So we've got to use the graph. So we're after X. So let's find out what wavelength that maximum occurs. So doing the line down, just being careful, that's pretty much on the line. So that's going to be 380, and that's in nanometers. So let's put our numbers into our equation. So we've got as the first order, so 1 times by 380 nanometers, so times 10 to the power minus 9, and that equals d, which we don't know, times by sine of the thing they tell us, 28.2. So if we solve that, we've now got d, the grating spacing, is going to be equal to 380 times 10 to the power minus 9 over sine 28.2. And that equals 8.04146 times 10 to the power minus 7. So that's in meters because that's the spacing between the gratings. So we're after the number of lines per meter. So therefore we have to do 1 over that. So capital G equals 1 over that. So 8.04146 times 10 to the minus 7. And if we do that, we'll get a final answer of the number of lines per meter will be 1, 2, 4. I should do this above the line. No, 1, 2, 4, 3, 5, 5, 4. Which to correct number of significant figures should be, I'd say 2 sig figs because we've used 380 and that's there. But basically 1.24, let's say 3 sig figs times 10 to the power 6. The next question is one of the hardest marks, 3 marks definitely, on this whole paper. And when I did this paper, I do them timed every year. I did not get 3 out of 3 for this. Happy admitting that. I'll talk through it. There is some good physics behind it. I still think the 3rd mark we'll come on to is a bit of a silly mark, in my opinion. So it says a scientist wants to obtain an accurate value for the difference in wavelengths between these 2 lines. They can either, so option 1, analyze the 2nd order spectrum, so n equals 2, from the original grating, or they can analyze the 1st order spectrum, so n equals 1, but from a new grating with double the lines per meter. So which options do we choose? Well, let's just figure out first what she's actually measuring. So she try and measure difference in wavelength. To do that, she measures the angle. So basically, we've got to look first at this equation. So n theta equals d sine, n lambda equals d sine theta, and rearrange it for theta. So sine theta equals, we've now got n lambda over D. Now for this particular experiment, because they don't really use D, we're using G. So G, as I said earlier, is going to be equal to 1 over D. I'm just going to rewrite this as sine theta equals n lambda G. So the two options then for this equation, so let's just do them one at a time. So for option one is if the second order spectrum is used, so therefore we're going to have n is multiplied by 2. So therefore sine theta is going to be equal to 2n lambda G. And then option 2 is going to be if G is increased, so G times 2, therefore sine theta equals, again, times by 2, 2n lambda G. So the reason I don't like this question is because which option should you choose? It seems like it's pretty much the same option, or it's the same difference for both options. So essentially, the angular separation or the angle measured would be the same for both options. Now, there is a subtle difference between them, which this is one I didn't pick up on when I first did this question, is that if you've got a number of orders, so if you imagine the sort of diffraction grating down here, the light going through it, and then you've got different orders around here. If you've got different wavelengths, which they haven't just got monochromatic light, so it's not just like all red light going through it. If you were to use like these different wavelengths, so let's say you had, I don't know, red wavelengths, blue wavelengths, etc., they would spread out a little bit. So you'd have like the red order, that wavelength would be over here, the blue one would be here, and same down here as well. So you have them at slightly different places. You want a quite bad diagram here of it, but basically the idea is the greater orders you have, the greater separation between the orders measured for different wavelengths. Don't forget, red diffracts more because it's got a higher wavelength, so therefore sine theta is going to be bigger. So essentially the final mark, which is that basically option 1, when you are measuring multiple orders, option 1, you are essentially going to get some of these maxima overlapping between each other. So we'll say that at higher orders, get rid of that, the maxima will, from different wavelengths, will overlap. Now that won't happen at the other option because you're just measuring n equals 1 and you've just changed the number of lines per meter. So that's what the mark's for here. For one for sort of proving and one for stating that the angle will be the same for both, or the angular separation. And then that last mark here, which I think is really mean for realizing at higher orders, they would actually overlap. It's a bit of context. This is just like, one of the worst answered questions on the paper in the examiner's report. So learn from it, but don't beat yourself up too much if you didn't get 3 out of 3 on this one. Okay, question 4 starts off with talking about some deuterium-tritium reaction between two isotopes of hydrogen. It tells us the reaction here. You're not expected to have seen that before, but we're going to analyze the kinetic energy and momenta of the different particles. So the energy from the reaction is transferred to the kinetic energy of the helium nucleus and the kinetic energy of the neutron. So both these two here. Assume the kinetic energy of the hydrogen nuclei are 0 just before the reaction occurs. First question is, show the kinetic energy of the neutron represents 80% of the total energy transferred. So imagine all this energy in this interaction is 100%. Basically show that this is going to be 80% and this is going to be 20%. So let's first of all link. We've been in this question talking about kinetic energy and momentum kind of separately. We've talked about kinetic energy so far. We need to talk about momentum and conservation of momentum, okay? The reason we know that is because just like any other collision, we can treat it, as if it was two cars coming together or something similar. So what we have to do first of all is look at, we do know something about neutrons compared to helium nuclei. So the neutron has a quarter of the momentum of the helium nucleus. If we were to try and picture this happening, the interaction, they don't have any kinetic energies of hydrogen nuclei initially. So let's say they just combine. Basically what's going to happen is you're going to have the helium nucleus, so go in that way, and you're going to have the opposite direction, the neutron go in the opposite way. So we'd say the neutron has a quarter of the momentum of helium. Don't forget, these have to have, in conservation of momentum interactions, because there's only 2 particles being emitted, these two are going to have some momentum this way, and you're going to have momentum this way, which is equal and opposite, because that's how momentum is conserved here. So next we've got to relate to this all to kinetic energy. So kinetic energy and momentum. So we start off with the kinetic energy equals half mv squared. Now the trick to get this related to momentum is to know that momentum P is equal to mv. So we're going to rewrite this in a slightly different way just to get momentum into it, basically. So we're going to write, basically, we're going to square the m and then put an m underneath. So that's the same thing if I keep v squared as it is. When I do that, we then find that the momentum, which is mv, we could rewrite this as p mv squared, because m squared v squared is the same thing as momentum squared, and again it's still divided by m. So what this shows us is the relationship between kinetic energy and mass is going to be the fact that they are inversely proportional. So kinetic energy is proportional to 1 over m. So it means if the neutron has a quarter of the mass of the helium nucleus, what that means is then it's going to have 4 times its kinetic energy, because those two things are inversely proportional. So therefore it's got a quarter of its mass, so it's going to have therefore 4 times the kinetic energy of the helium nucleus, which is what the question is asking to show. It's got 80%, so 80% for the neutron, 20% for the helium nucleus, which is obviously a 4-to-1 ratio, so 4 times bigger. Next down below, we've got, so the last question was a show question. Almost always you've got to use that in the next question, and it's no different here. We're told the combined kinetic energy of the helium nucleus and the neutron is 2.82 times 10 to the minus 12. Calculate the initial speed of the neutron. So let's go back to our kinetic energy equation. We do know the mass of a neutron because we have our equation sheet or our data booklet, and the kinetic energy is 80% of this number here. So for kinetic energy, we're going to do 80% of 2.82 times 10 to the power minus 12. Equals half, and the mass of the neutron is just on your data sheet. So this number here, 1.675 times by 10 to the minus 27, and the speed squared, or the speed is what we're trying to find. So solving for v, we're then going to have big square root of whatever this is, divided by half, or I guess times by 2, same thing, times by the mass of our neutron. So if you stick all those into a calculator, we should get a speed which is reasonable, which rounds to 5.2 times 10 to the power 7 meters per second, which is very big, and it's over 1/10 the speed of light. However, particle interactions often release particles traveling at really high speed, so that shouldn't strike us as too weird. It's a very short question, that one. This one is hard to hit the mark scheme for, I think, in my opinion. However, this is very standard, so you should be hitting at least a couple of marks there. Next up in this paper, we've got some mechanics questions. So we've got a quite complex sort of situation here where we've got a object O, which is getting transferred across a river. We've got some sort of cables connecting it to 2 posts, one's higher than the other. And we're asked to work out a little bit later a few different things about the forces and how the work done on it due to friction, etc. is. I'm going to label this here now. This is the really key bit for the next question, is the weight of this object is 350 newtons. And the tension in the ropes, because the weight's going down, tension is going to be acting here, and it's going to be acting here. So over on the next page, we are given a scale drawing of this. It says, figure 4 is a force diagram drawn to scale. It represents the magnitudes of T1 and T2, like I've just drawn, where O is at rest. In its position, resistive force is 0, so we're assuming no friction. Go on to complete the force diagram, work out the magnitudes of these two. So it is to scale. You have to be able to draw scale diagrams for A-level. I know often you want to do Pythagoras or do trigonometry. You have to be able to do scale drawings as well. So I'm going to show you how to do this one, okay? So I'm going to do a rough diagram over here, then I'm going to do it to scale over here. So if I've got the weight of the object acting downwards, so this is my object O, I've got the weight acting downwards on it. I've got these other two forces basically acting upwards. If I knew the angles, I could do cos and do trigonometry, but actually the scale drawing is probably a bit quicker, I'll be honest with you. If you were to complete the sort of force diagram, basically we'd end up with a closed triangle because all the forces are in equilibrium. So if I was to draw them out tip to tail, so let's do this one goes to here, and then obviously this isn't perfectly to scale, but then this is T2, then T1 goes over to here, and then we'd find that the weight is going to sort of act in like that direction, okay? So what we have to then do is to essentially either do this as a tip to tail diagram, or easier, because they've already drawn out for us, make it into a parallelogram of forces. So parallelogram of forces, you will have learnt this definitely at GCSE as well as at A-level, is if I've got two forces at an angle to each other, if I complete the parallelogram and draw a resultant force from one corner to the other, to scale, that's going to be equal to the resultant force. So I'm just going to do the same here. So I'm going to do it with pencil and ruler, obviously, because it's to scale. We have to make sure we're really careful with our drawings. Okay, so I've drawn in my parallelogram to scale. I measured the sides first, just so I can make sure that the parallelogram sides opposite are exactly the same. So to complete this then, I'm finding, like I did over here, from one corner to another, what is the resultant force. So I've completed this down here. We're going to have the weight going in this direction, and weight goes directly downwards. That's another tip, you know you're right. So what we've got to do is to figure out measure what W first of all in centimeters, then figure out what scale they've been using. So I've got this to be 3.5 centimeters, maybe almost 3.6, but 3.5. Now, if you look back on the previous page, I highlighted it earlier, the weight of the object they actually tell you is 350. So therefore weight is going to be equal to 350, and that's 3.5 centimeters. So the scale works out quite nicely, actually. You could say then 1 centimeter is going to be equal to 100 newtons. So the question asks us to find the magnitudes of T1 and T2. So with my measurements here, we're just going to convert that scale. So using that scale then, I've got T1 is 4.8 times 100. So 480 newtons, and I've got T2 is, I've got 4.1 times 100, gives me 410. This one on Mark scheme says it's 400, but 410's in the range, so that's absolutely fine. This one, you get basically 20 newtons each way, sorry, 10 newtons each way for each of these different measurements. Moving on to the next question. This is a little bit trickier, I would say personally. We've got 5 marks, so big long calculation, looking at this diagram, which is annoyingly on the previous page. So I'm going to keep referring back to it, and let's highlight some stuff for what's going on in this question. Okay, so in this question, it says it's a second test, so it's a slightly different situation to before, and this thing is now released, it's now not stationary, and P&O move along the cable to B. So essentially what's happening, it starts up there, and it goes all the way to B. The whole thing is it's used to transfer supplies across the river, so it goes from A to B. We have a change in height in the center of mass between A and B, so 4.5, so it goes down by 4.5 meters between the two. And we also have the distance traveled along the cable is going to be 18. So sort of diagonally, that's going to be 18 meters. The speed when it reaches B is going to be 6.5. So we've got S there, we've got a V there, meters per second. Just calculate the average resistive force on O and P as they move from A to B. If you don't know where to get started with this question, I'd always try and work out something that is correct. So there's a kind of obvious thing to work out first of all, which is if we've got a change in height and we know we can work out the mass of the object, quite often that's because they want you to work out the gravitational potential energy. Okay, so let's just do that first. Now the mass of the object, we don't know, but we do know the weight. So the weight from the previous question was equal to 350 newtons. So obviously weight equals mg, so m equals 350 over g. So we can find out the mass of the object nice and easy just by working it out, and that's 336 kilograms. Next then, let's work out the gravitational potential energy that lost as it goes from first position to its second position. So we've got gravitational potential energy equals mgh. So 36 times by 9.81, or I guess I could have just left that as the weight, couldn't I? Times by 4.5. So we stick down to our calculator, we get that automatically is 1575 joules. So that's already a couple of marks, even we haven't got close to solving the question yet, just for the things you can work out from what's given to us in the question. Right, next let's go on to the tricky bit. How do we get this velocity involved, and how do we then use that to get a resistive force? So the velocity is going to give us the kinetic energy. So we start to talk about energy here. If I was to work out the kinetic energy, that's the kinetic energy gained as it is stationary and it starts speeding up and it gets to B, it's going to have a velocity. So I can work that out as well, because now I know the mass. So half mv squared, I've got half 36 kilograms times by the speed squared, so 6.5 squared. And that's going to give us another value for energy, and that's 754 joules. So I've got two values for energy, and I'm from working out the mass. Now let's just picture what's going on here. So it's losing gravitational potential energy as it's dropping from one height to another. It's gaining kinetic energy as it's speeding up along the slope. The question is about resistive forces. If there were no resistive forces, then the potential energy would be lost would equal the kinetic energy gained. However, that's not the case because there are resistive forces. So what we have to then say is the work done due to friction is going to be equal to, so to resistive forces and friction is going to be equal to the loss in gravitational potential energy minus the gain in kinetic energy, because they would be equal if there was no resistive forces. If there's a difference, we have to work out the difference between them. So we're just going to work that out now. So my potential energy, so 5 for 1,575 minus 754, and that's going to give us 821 joules. And the force we're after, that's the work done due to friction. You might be seeing where we're going with this now. The one thing we haven't used is the distance traveled along the cable. So we can do work done equals force times distance, and say that the force is going to be equal to the work done divided by distance traveled. So 821 over 18. And if you put that onto a calculator, we should get the overall resistive force is 46 newtons, which sounds kind of reasonable for our fifth mark there. Finishing off this question, we've got a much more simple question, in my opinion. This could come up at GCSE as well. It's the same sort of mark scheme. It says, the bag contains a fragile item packed in a suitable material. How can the material prevent damage to an item when it stops suddenly? So when it stops, meaning basically there's an impact or there's a collision when it gets to B. So there's a couple of different approaches named in the mark scheme. I think by far the easiest one is that the material is supposed to basically cushion the landing by increasing the time taken for the impact. Just like an airbag in a car, you want to try and increase that time taken so you protect the thing inside. So why does this make a difference then? We've got to then use the equation, so force equals change in momentum over time, or rate of change in momentum. So basically we'd use that equation. That doesn't get you marked just for quoting it. We've got to use it in context. So we'd say basically, the force is, we say rate of change of momentum. And from this equation, if I increase time, it should be obvious that force is going to go down, assuming the change of momentum is constant, which it would be because you're just adding a packaging, you're not changing the journey of the actual object. So we'd say for a constant change of momentum, I'm just going to say mv here because I've said it already, time is inversely proportional to the force, or you could write that out in words if you want to. So to the force. So as time increases, the overall force experienced would decrease. Other approaches allowed in the mark scheme here are to talk about the work done is equal to change in sort of kinetic energy. You could talk about Newton's second law, which essentially this kind of is, but that's my favorite approach because it's probably the one you learned at GCSE. And in my opinion, is the easiest to understand. Okay, next we're moving on to electricity questions, which in my opinion are not that terrible. This one's definitely not that terrible. So we've got a circuit in this question, which is used as part of a temperature sensor. So it's got a thermistor in it. We've got an EMF of 6.5 volts, negligible internal resistance. Hooray. Then we've got initial temperature as 22 degrees. We'll use that later. It says that the temperature of the thermistor, the resistance is 350, and there's a current in the circuit of 12. So we're asked to calculate the resistance of the variable resistor. So first thing to do is to work out the overall resistance, because that can then help us to work out the resistance of just the one. So the total resistance is going to be equal to the PD, or EMF in this case, because it's a negligible internal resistance, divided by the current. So 6.5 divided by 12 milliamps in regular amps, which is going to equal to 54, 1.6 recurring. So go around it there. So we know if this is then 350, so this is 350, we don't know what this is. It means the total resistance is that. So therefore we'd find the resistance of the thermistor, which is resistance to the variable resistor, sorry, which is the total, so 541.667 minus 350, which is going to give us 191.6667. I'm just going to round it to two significant figures because most of all the values are two significant figures, and the lowest is two significant figures, so therefore there should be two. Next question, you're looking at me thinking, I thought you said this question was easy. This looks horrific. However, once you've done natural logs and logarithms, which you will have done by year 13, this is not as bad as it seems, I promise you, okay? It's a kind of equation you've never seen before. Hardly any students would have seen this before. You're not supposed to. It's not required practical, but we can use the information in the question to work it out. So it says the resistance R at temperature theta is given by this equation. R0 is the resistance at the initial temperature. The temperature is increased to 318. The variable resistor is the current is still the same, and the potential difference is now 3.2. So we're asked to determine what B is. So first things first, we're going to plug loads of values in here, but we can't do it at the minute as it is. So we know, I'm just going to write down like you would do with Subat equations. We know the temperature of the resistor now is 318 Kelvin. We do know what it was initially because it was on the previous page. It was 22 degrees, the initial temperature. So we've got to convert that to Kelvin. So 22 plus 273 is going to be equal to 295 Kelvin. Next, to work out the resistance, the final resistance, so what it is now, it says the current is 12 milliamps and the potential difference is now changed to 3.2. So I'm just going to do V equals IR again, so 3.2 this time over 0.012, and that's going to give me our resistance now of 267 ohms. So other things we do know, so R naught is on the previous page again, because this time we're looking at the thermistor. So the thermistor resistance, it says it's 350. So we don't need to work anything out there. That's just 350. And once you've done all that, we essentially have every value in here we need. So we plug in our values and we just make sure we're keeping an eye on like how to get B down and our log rules, and then we should be okay. So I'm just going to do one step with it all in, and then I'm going to show you how to rearrange it. So we've got, actually, you know what, I'm going to rearrange it straight away because I think that's easier because say write out loads of numbers multiple times. So I've got R equals R naught times by E to the power B, and 1 over the temperature now minus 1 over the temperature at the start. So to get B down, we've got to take natural logs of both sides. So I'm going to then do R naught comes over to this side, and then I'm going to do natural logs of R over R naught is equal to, so B, just my exponent here, 1 over that minus 1 over that. Okay, so to find B, I then need to, once I've got ln R over R naught, I just divide that by this expression here, and that'll give me a final answer. So now we've got to do is plug our values in. So I'm just going to do this over here because I'm running out of room slightly. So B therefore equals, so ln R over R naught, which we said R was 267, R naught was 350, over 1 over the temperature now, which is 318 Kelvin, minus 1 over the temperature at the start, which was 295. If you put all those values in, should work out to be, it's 1,104 or 1,100 if they are, if you're rounding it to two significant figures, which we probably should do. So I'm going to get rid of this final one because everything's in two significant figures in the question, or the lowest is two significant figures in the question. Now, the last question is what the unit is. So for the unit, you kind of have to like look at what the what's in the original equation. So we've got R over R naught here, so that cancels, and there's natural log of that. Down the bottom, this is going to be, because it's 1 over the temperature, this is going to be K to the minus 1. So B going to be equal to 1 over K to the minus 1. So 1 over K to the minus 1 is obviously just K, or Kelvin. And the final follow-up to these questions are all about why the current needs to be controlled. So the current needs to be controlled in the circuit. The idea is with lots of electricity practicals, if you don't keep the current the same, then the resistance of the circuit is going to change because the temperature is changing. So as electrons go through, if the current's changing by a significant amount, then the resistance will change because the ions will be vibrating in the metallic lattice, meaning the temperature is changing, meaning the resistance changes, which we don't want to happen. We want the resistor to be a result of the temperature changing due to its surroundings. So basically the current in the circuit causes the thermistor temperature to change. We don't need to say whether it increases or decreases here, although you can do. So that causes it to change. And then as a result, basically, you're then going to have the thermistor. Don't forget, thermistor's resistance depends on temperature. So thermistor's resistance will decrease as temperature increases. I'm just going to write temp there, so I've not got room. So like with this graph here, so temperature and resistance is that relationship, which we need to know. 6.4 looks like a horrible question. Trust me, it's really not that bad. So it says, explain how ammeters and voltmeters can be used in the circuit to demonstrate conservation of charge and conservation of energy. So in this circuit, basically conservation of charge is essentially to do with, the hints there, there's an ammeter. Conservation of charge is to do with current, and conservation of energy is to do with voltage or potential difference. So I'll explain what I mean in a second, right? So let's say I've got a series circuit. We know current in a series circuit should be the same at each point. So I can't spell current, but current should be the same at each point. Whereas PD, we should know, is going to be split or shared evenly, not evenly, sorry, is split, shared between the components. So that overall it's fixed, but it's shared between the components. So how do I prove that? Let's do the current one first. So I just place ammeters at positions. So it says X, Y, and Z. So just any of those positions, X, Y, and Z. The current should be the same, as we just mentioned, equal at each point. So therefore, charge is conserved. If you want a bit of extra detail, we know that current is equal to rate of flow of charge. So if charge is conserved, then current has to be the same at each point. Next one we could talk about is the potential difference. So I could place a voltmeter this time. This time I'm going to go, it's a little bit tricky to explain this one, a voltmeter across this and a voltmeter across this, and then I'll do one across the whole thing. And if that plus that add up to the one across the whole thing, it shows that energy is conserved and the PD in a series circuit is split. So basically you place voltmeters across X to Y and Y to Z, and also across between X and Z. And you say the PD should be equal to, basically the PD across X to Z should equal the PD across X to Y plus the one across Y to Z. You can phrase that differently. I've just used the letters here and I'm running out of room slightly. And that would show that energy is conserved. And again, the explanation behind that is because potential difference is equal to energy or work done per unit charge. So if energy is conserved, that means the voltage doesn't get lost anywhere. Next up, we've got some waves questions. So here we've got a stationary wave on a piece of string, and we are given loads of information. We have the length is 1.05 meters, and we've got the frequency of it, and we've got a graph showing its displacement with distance. So not with time, but with distance. This is like if you're looking at it in front of you. The first one says describe the amplitude of one of the progressive waves. It tells us they're formed by two progressive waves traveling opposite directions. That's how stationary waves are formed. So the amplitude of each one, because we should know at the point where the antinode is, so right at the peak of the wave, we know the two amplitudes have basically the two individual waves have reinforced. So if I've got two waves reinforcing, that means that the overall resultant amplitude is going to be twice as high if they have the same amplitude to begin with. So therefore, it's going to be 2 times the original amplitude. So all I need to do is look at the displacement of an antinode. So this halfway between 6 and 8, so that's 7 millimeters. So therefore, the original is just going to be half that. It's going to be half of 7 millimeters, and you need it in millimeters. So we just say it's 3.5 millimeters overall. Okay, next one is to work out the speed of these progressive waves. So from the graph, we should know we've got V equals F lambda. We could figure out the wavelength because that's one full wave. That's halfway between 6 and 0.6 and 0.8. So that's going to be our wavelength, so 0.7. And the frequency is in the question. So this is actually quite a nice 2 marks because you just do frequency times by wavelength gives you the overall speed. So that's going to get you 437.5. Or let's round it because we've got only a couple of significant figures in here. So I'm going to say 440. The phase relationship when t is 0 between the two waves. So when t is 0, it says here, this is basically, we're talking about this graph. So like we mentioned earlier, for the amplitudes to constructively interfere and to reinforce for superposition to occur, these waves have to be in phase for this whole thing to occur. Otherwise, it just wouldn't happen. So therefore, we say they're in phase, or you could say there's 0 phase difference between them. That would also be fine. Next, we're asked to show how the displacement of S varies with T. So be careful with questions like this. This is not talking about the whole wave. It's talking about this point here. So hopefully we can see with a stationary wave, not all particles oscillate with the same amplitude. The ones at the nodes don't oscillate at all. The antinodes will go up and down with 7 millimeters. This one here will go up to -4, back up to 4, and so on and so on and so forth. We need to know the time period. This is slightly different. This has time on the x-axis rather than distance. So we need to be able to work out the time period. Luckily, that's quite straightforward because the time period is just 1 over the frequency, which is 1 over 625. So if I work that out nice and quickly, that's 0.0016, or I'm going to put it in milliseconds because that's what the graph asks for, 1.6 milliseconds. So I'm just going to make a note of that here. So that's my time period. That's how long it takes for one full oscillation. We have to make sure it starts at 4, positive 4, because that's where it starts at. Time is 0. And I'm going to do this with a pencil because I'm scared of going wrong here. So 1.6 is there. 0.8 is going to be here. So let's then draw that out. So it starts at its peak. It's going to go to the bottom here. So it should pretty much pass through about there. And then it's going to come back through to where it was originally after 1.6 seconds, 1.6 milliseconds. And then we've got to continue because that's what the question asked for. So 1.6, it gets to 2.4 by the end. It's going to go back down to where its negative amplitude was. So down here. I've gone slightly wrong there. That shouldn't be quite so curved. I'd rub that out and do it again. But that's basically the shape of it. Top tip with graphs, make sure you take your time. This one's 3 marks. Don't just guess it. There's always something to calculate. And then you've got to be nice and accurate, like I've tried to be there. Let's pretend that a little bit didn't happen. That's the end of the main section. Now we're on to the dreaded multiple choice section. So for each of these questions, I'm going to go relatively quickly. I'm going to pause on ones that I think should take you a little bit extra time. Good tips on multiple choice questions is to make sure you leave some till the end. So there'll be some that will take you sort of 2, 3, 4 minutes. So leave those till the end. If you've got time to do them, great, but make sure you get the easier ones first. So first up, we're after some specific charge. And we've got our nuclear changes. 4 different nuclear changes result in the nucleus with a greater specific charge. So specific charge is the charge per unit mass. And it's not just as simple as looking at these nuclei. We have to then figure out what would, after each of the decays or things that happen, what it would be next. So alpha decay, I'm just going to write them down here. So alpha decay, we would have, we don't know what element it is, but it would be 80 at the bottom, and it would be 205 there. Next one, beta minus. Beta minus, we should know you gain a proton. So I now have 13, and then I have 28 at the top. And this one, beta plus, I lose a proton. So I would start off with 20. Now I've got 19 and same mass number. And this one down here, electron capture, is kind of similar to beta plus decay in that you lose a proton and it turns into a neutron. So the mass number stays unchanged. So for electron capture, we would have, again, the loss of proton with no change in the electron. Now, you don't have to get a calculator out and work out the exact charge and exact masses because we're just looking for ratios here. Essentially, I'm looking for which ratio here has the greater specific charge. So this one is obviously going to be 80 over 205. This one's 13 over 28. This one's 19 over 39. This one's 46 over 105. So having a look at each one of those, you can stick them to calculate if you want. However, hopefully we can see this one, number C, is actually pretty close to a half, whereas the other ones are nowhere near a half overall. So therefore, I mean, that one's slightly bigger than that one. That's the second closest. It's going to be option C in this question for the specific charge. Moving on to this photoelectric effect equation, there's quite a lot to read here. It says there are 2 experiments done separately. Variable frequency is incident on 2 metal surfaces, and the work function of X is greater than the work function of Y. That's the only difference between them. Which of the following graphs show how the kinetic energy of the electrons varies with F? So there are 2 we should be able to discount straight away, which is these 2. So in these graphs, when we've got kinetic energy varying with the frequency of the EM radiation, we should know. So the graph is a really good graph to learn is that the graph looks like this, and that the gradient of it is going to be equal to Planck's constant, or H. Now that's a constant, so the gradient of these graphs cannot change. Something else to learn from this graph here is that this bit here, that is called the the threshold frequency at which photoelectric effect starts. And this y-intercept here is going to be negative, the work function. So even though these don't have a negative part to the graph, we could figure out basically that the fundamental frequency, the threshold frequency, so E equals HF, HF equals the work function plus kinetic energy. When there's no kinetic energy, basically when that's that y-intercept, so when the y-axis is 0, F naught is going to be equal to the work function over h. So essentially, threshold frequency is proportional to work function. So therefore, if the work function of x is greater, that means the threshold frequency is going to be greater along this axis as well. So it could be a bit higher up. So therefore, that means it's A, because it tells us x is bigger than y. Now, that was a relatively straightforward photoelectric effect question. This one is trickier, and this caught me out when I did the paper myself timed. I got this one wrong. I'll tell you how I got it wrong. So it's got monochromatic light, so means same frequency. So frequency is the same on a surface. The photoelectric current is the rate of flow of charge from the surface. So essentially, light goes in, electrons are emitted off, and they go into a circuit and cause a current to flow. We are measuring the kinetic energy and the current, and it says the frequency is then increased. Don't know why I put that down there, but the frequency of light is increased, and there's no change to the rate at which energy is incident on the surface. So the energy that goes in a certain time frame is the same or is constant. It says what will happen to the kinetic energy and current when frequency is increased. It should be obvious that the kinetic energy goes up, so the kinetic energy the electrons have is going to increase. However, I said initially that the intensity does not change, and that's incorrect. I'll explain why. So if the total energy is constant, now energy of each photon is equal to hf. Now for the total energy, we need to know hf times by the number of photons. So if the total energy is constant for an increasing frequency, so it tells us f goes up, there has to be less photons hitting the surface. That's only because of this bit here. There's no change to the rate at which energy is incident on the surface. That doesn't say each photon, that just means the total rate. So frequency goes up, that means the number of photons goes down, and that means essentially the intensity of the photons hitting per second goes down. If intensity goes down, there's less electrons being emitted, so I decreases. So it's actually option A. So here we've got a ratios question, two ratios questions, all about the photons and wavelengths. We're asked to work out the ratio between the wavelengths for these two energy transitions. So E equals hc over lambda. Now, speed of light is constant, h is constant, so energy is proportional to the inverse of the wavelength. When that happens, we need to be able to rearrange this in a way that's useful for us for the energy levels we're given. So I could say energy times by the wavelength is constant. If that's the case, then I've got energy of 1 times my wavelength of 1 equals energy of 2 times my wavelength of 2. And then if I want to find this, I should rearrange this for lambda 1. So divide by lambda 2 equals E2 divided by E1 because they're inversely proportional. So effectively, once we got to that point there, you know what E1 is because E1 is 5 electron volts and E2 is 15 electron volts, just because of the numbers that are here. So therefore, it's going to be 15 over 5, which is equal to option C. The next question is similar. It's all about ratios again. This time we've got an electron and a proton, and we're after the de Broglie wavelength. So de Broglie wavelength equation is h over mv. They move at the same speed, so we can ignore that, and say that these two things are inversely proportional. So in the same way up here, I'm not going to do the whole thing, but what we could say is that if I've got the ratio of the wavelength of the electron over the wavelength of the proton, that's going to equal the mass of the inverse, so mass of the proton over mass of the electron. So you can either get your values from your equation sheet, or you probably remember from GCSE, the proton's about 2,000 times more heavy than the mass of the electron. But either way, the ratio between mass of proton and electron is about 1,800 if you plug in your values from your equation sheet. This is quite a common type of question. We are given for number 13, a laser emits wavelength light of 600 nanometers for 10 nanoseconds. Basically, how many waves are emitted by the laser. So we need to work out with the wavelength, because we know it's light, we also know that speed of light is equal to 3 times 10 to the power 8. So what we can work out is the frequency. So frequency is speed divided by wavelength. So 3 times 10 to the power 8 divided by 600 times 10 to the power minus 9, because it's nanometers. So the frequency in this case is going to be quite high, but 5 times 10 to the power 14. Now, why are we working that out? Well, once we work that out, we can then work out the time period. So time period is 1 over that, and the time period means the time for one wave. So one wave, if I do 1 divided by 5 times 10 to the 14, gives me 2 times 10 to the power minus 15. So that's the time taken for one wave. and the total time I've got is 10 nanoseconds. So the number of waves is just going to be equal to the um, the time that the laser's on for divided by the time period of 1. So 10 nanoseconds divided by 2 times 10 to the power minus 15 is going to be equal to 5 times 10 to the power 6. So option D. Question 14 is all about polarization. We're asked to measure the intensity of a light source from S1. Polar material is placed between in the detector. When the material is rotated, the intensity does not change. So that's S1. Then it's repeated for a second source, the intensity decreases. That's S2, which is correct. Well, when you rotate it, if the intensity doesn't change, that means the light is unpolarized. But if it does change, it means it's polarized. So therefore, it's just option A. Next question, we are given a loudspeaker which says a sound is mounted to a tube filled with water. A tap at the bottom of the tube is opened to allow the water to run out. So there is water. This is a solid. The wave cannot travel through this bit. A student observes the change in loudness emitted by the tube. And when the length of the column reaches L1, so that's this bit, so when the water's up to this bit, the loudness is at its maximum, then you decrease the water and the next maximum is experienced here. So the question says, what is the wavelength of the sound? These kind of questions can look really tricky. This one is not too bad, I promise you, okay? Now, because this sound must end here when it gets to the water, when the water is up here, the sound must end, because it's reflecting back, because it's a stationary wave, it must end at a node. So there'd be a node there. Then when the water goes down, it must then end at another node, because it has to reflect back. So effectively, what it's saying is that we know that the distance between two nodes on a stationary wave is going to be equal to the difference between these two. So that would be equal to L2 minus L1. Now we should know for a whole stationary wave, so I should do that dotted, shouldn't I? A whole stationary wave, one wavelength is 2 loops, or basically 3 nodes. So therefore, if I've got the distance between 2 nodes, that's just going to be wavelength over 2. So wavelength over 2 is going to be equal to L2 minus L1. So therefore, to find the wavelength, I would multiply that by 2, giving me option D. This next kind of question comes up a lot as well. We've got a sound detector that's moved along a line PQ. There are maxima recorded and there are minima recorded. It tells us where they are, so I'm going to write them in because that will help us. So we've got maxima at W and Y, and we've got minima at Z and at X. And the question's again asking for what the wavelength is. So they give us loads of different options here. Basically, what we're looking for the wavelength of the sound, it's got to be the path difference. So when the waves travel across from S1, let's just say, for example, they go to the first maximum, the path difference is going to be equal to, for each one, the difference between the path differences. This one would have traveled one more wavelength than this one because it's slightly further away. So if the path difference is going to be equal to the wavelength. It could be the difference between maximum and maximum. It could also be the difference between minimum and minimum. Either one works. So we're going to sort of ignore the S's for this one. We're going to look at which ones we're given here to figure out which one's which, because 3 of them are between maxima and minima, and the 4th one is between a maximum and a maximum, or a minimum and a minimum. So the A is actually the only one. So this is X to W. So X to W, that's min to max. Y to X, that's min to max. Z to W, that's max to min. This is the only one where it goes from a maximum to a maximum. And these terms here are just telling you about the path difference, what it is. The key knowledge here is that the difference between path difference between a maximum and maximum has to equal one whole wavelength. So therefore, it's option A. This question is about Young's double slit. So we're going to write down the equation. So we've got the width of the fringes that are observed is equal to the wavelength multiplied by the distance from the fringes to the screen divided by the slit separation. So it says the separation of the fringes, so W, can be increased by any of these following options. So let's just go through the obvious ones. If you decrease the width of the single slit, that doesn't affect it. So it's a single slit, then it goes through a double slit. The single slit just makes it coherent. That doesn't affect anything here. Increasing the separation of double slits, well, that's going to decrease W, so that doesn't work. Decreasing the distance, that also doesn't work. Now, I'll tell you why it's A. So it says they'll have lower frequency. If you've got a lower frequency, we know that that means you're going to have a higher wavelength and vice versa. So lower frequency, higher wavelength. So that actually is going to cause W to increase. So therefore, it's option A. Sorry, I just whacked my camera there. Okay, so we've got a block on a slope, which has got lots of forces acting on it. We've got a force acting this way, And it says the block is accelerating, so accelerating up the slope. So let's resolve forces first to figure out what the magnitude of the acceleration is. So the first one to do is this F. I'm going to draw out separately because I've got beta. We're trying to resolve up the slope. So therefore, I've got this and this. So we are looking for the adjacent. So therefore, I'm going to find that's going to be F cos beta up the slope. Next, I've got the weight, which isn't drawn on. So the weight goes down here. This is just a very standard resolving components of a inclined plane. So I've got the weight mg go in this direction, and I'm trying to resolve it into down the slope. So that's this one here. Now this angle is the same as alpha. So therefore that's alpha. And this is now the opposite. So I've got this expression here is going to be mg, because this is equal to mg times by sine of alpha. So because it's accelerating up the slope, there must be a resultant force in that direction up the slope. So therefore, for the final overall force, what I'd say is this going to be F cos beta minus mg sine alpha. It doesn't ask us for the force, it asks us for the acceleration. So acceleration equals F over m. So if I basically divide everything by m, so here I have A equals, and that goes divided by m, the m cancels from there. We are left with option B. So cos F over m cos beta minus g sine alpha. Okay, for this moments question, I've drawn a couple of things on to make it a bit simpler. So what we've got to do, if it's a moments question, we've got the pivot here. We've got the center mass of the bar going downwards, which isn't labeled, but it does tell us it in the question. We've got a weight here, and we've got tension going upwards. So we're trying to work out the moment. So first of all, we do the weight. I'm going to call this x. You could just put a number on it if you wanted to, but that's halfway along. That's the distance x. The reason I do that is because the weight here is twice the distance away. So therefore, I call that 2x. These are the clockwise moments. Anti-clockwise, I've got t, but t we have to resolve into its perpendicular component, perpendicular, so to the actual direction of the beam or the thing we're acting around. So we're then going to say that, I've drawn the triangle up here. So this is t. We're looking at the component going upwards in this triangle. This is theta because of corresponding angles, and therefore this is going to be t cos theta. So this is t cos theta multiplied by x, because that's the distances away. And it also tells in the question, T is going to be equal to, the tension is 4W. So we're just going to relabel this as 4W before I forget later. So let's simplify things down. X was only there to help us like sort of conceptualize what's going on. So therefore I can just cancel through, there's X in every term. So we're left with, we've got W plus 2W equals 4W cos theta. So therefore I've got 3W equals, well, 3, I can cancel the W's now, equals 4 cos theta. So therefore theta equals cos, inverse cos 3 over 4, which if you put in your calculator, that rounds to being equal to 41 degrees. So option A. Next up, we've got a projectile question, which I think this is quite tricky. There's quite a lot of workings out to do here, even though there aren't really any numbers. So projectile is fly from the ground over horizontal ground. Its initial velocity is u and angle theta. The range is d. There's a second projectile with everything's the same apart from its velocity 2u. Question is, what is the range of this projectile ignoring air resistance? So what we've got to do first of all is figure out basically the horizontal and the vertical components basically, and see which one is made a difference to. So just like an AC-BAT problem, it's probably helpful just to write down what we've got and what's different, okay? So with projectiles like this, where they sort of go up and come back down, by far the easiest thing to do, in my opinion, is to split the journey into halves, so that vertical final velocity for the first half is going to be equal to 0. Now for our second projectile, the initial speed is going to be equal to, so it's u sine theta. So for our second projectile, it's at 2u, so therefore it's 2u sine theta. Now our distance then in this case, if you now its distance, we don't really know anything about the range. We know obviously A is going to be equal to G. If we were to work out the time taken, we could do V equals U plus AT and sort of rearrange. So T equals V minus U over A. So because the V is 0, effectively, you're going to have, we said that U was twice as big. So now I'm going to have 2U up here and A is 0. So effectively, the time taken is proportional to U in the vertical direction. So therefore, if I've got twice the speed, I'm going to have twice the time. Bear that in mind for later. Horizontally, there's only one equation to use. We're now looking at the horizontal distance. So S equals UT or VT. It's the same throughout. Now, this is a bit simpler, this one, because we're looking at horizontal distance. We said the speed is going to be double, and the time is also going to be double. So effectively, you've got twice the speed. And from working out vertically, bear in mind the time is the same vertically as it is horizontally. I've got both of them are twice as big. So therefore, 2 times 2 means the horizontal distance is going to be 4 times as big. So the option is D. Got another projectile question for part 21. So this has got a massive acceleration in it, but don't be afraid. It's the same. We can treat it the same as we do with any other projectile problem. So a particle is traveling horizontally, has initial velocity u. So this is just horizontally of 1 times 10 to the 7. And it's got a vertical acceleration. So it's going to form a parabola just like any other projectile. But after the horizontal distance the particle travels, when its vertical displacement is equal to 8 times 10 to the minus 2, or 0.08. So just like any other CBAT problem, let's just do vertical. So S equals 0.08. U is 0 because vertically it has 0 velocity initially. The final velocity we don't know. The acceleration is this massive number here, 4 times 10 to the 14. And the time taken, we don't know. We try and find that out. So then we can work out the horizontal distance by doing speed, distance equals speed times time. So we're going to use S equals, my writing's awful today, S equals UT plus half AT squared. That cancels because U is 0. And we arrange this equation. So S equals half AT squared. So therefore T equals 2S over A all square rooted. And this is just vertically. So we know that this is square root of 2 times by 0.08 divided by the acceleration, which is 4 times 10 to the 14. So let's just work that one out. So that equals 2 times 10 to the power minus 8 seconds. Then because time's the same in both, we can say that S equals horizontally the initial speed times by time. So the initial speed was 1 times 10 to the power 7 multiplied by the time, which is 2 times 10 to the power minus 8. So that, put it down in your head, that is going to equal a horizontal distance of 0.2 meters, which is option A. This question massively caught me out along with lots of other students in this paper. It's all about an object thrown vertically. So far, so simple. It reaches maximum height at time t, capital T, and then reaches its terminal speed or terminal velocity on the way down. The object's acceleration is a, so on the y-axis here, which graphs show how its variation of a varies with t. So the thing is, you can't ignore air resistance. If you could ignore air resistance, then its acceleration would just be constant throughout. However, we're not ignoring air resistance here. So let's think carefully about what's going on. So when the ball is projected upwards, the acceleration is acting in a downwards direction because that's g slowing it downwards. So you've got g going that way. As well as that, you've also got air resistance acting in that direction as well, or drag going in that direction. So therefore, the deceleration as it goes upwards, or the acceleration basically, is going to be equal to slightly bigger than g, because drag is also acting to slow it down. So you could actually solve that pretty much straight away and figure out which of these graphs initially has a higher acceleration than g, and that would be option B. I'll explain the rest of the graph though. So initially that acceleration is going to be higher than g because there's drag slowing it down, or air resistance slowing it down, as well as gravity. Then it reaches its maximum height here, and it says it reaches terminal speed on the way down. I don't really know why they tell you that, because there's none of these graphs have anything after part T, but maybe it's just to remind you guys that air resistance exists. So if it has a terminal velocity reached on the way down, it will basically decrease after this point, but the idea is that acceleration is going to be bigger than just 9.81 because there's drag acting, so therefore it's option B. I'm going to do some drawing for this one. So if you were to stand on some scales in a lift, depending on when the lift is going, the scale reading on the scale will change slightly. That's because scales don't actually measure mass, they do measure weight, and then they sort of convert it back into mass. Now the forces acting on the scales, you've also got the weight of the person, mg, going downwards. Then you've got the reaction force going upwards, and that's what the measurement on the scales is actually measuring. So weighing scales basically measure R, they don't actually measure a person's mass. So knowing that, let's look at some figures we've got. We've got the mass of 75 kilograms, and the lift is accelerating upwards at 2.6 meters per second. So what we're going to do, because it's accelerating, we can basically equate forces on this side and say they're equal to ma. It's accelerating upwards, so we do r minus mg. So r minus mg equals ma. We're trying to find the reading on the scales. That's r, as we just mentioned. So therefore, we can put mg onto this side. So ma plus mg, and we can factorize out the m if we wanted to give us that. After that, it's just a matter of plugging numbers in. So we know the mass is 75. Acceleration is going to be 2.6, and acceleration due to gravity is 9.81. So we put all those into our calculator. We should get a value of 9.31. You could potentially work this out just by knowing the situation. The weight normally of this person would be roughly about, just under 750. However, because he's accelerating upwards, we should know that the reaction force is going to be a bit bigger because it's in that direction. Okay, in this next question, let's look at what we're given. So we're given force, we've got velocity, and we're after the mass of the air that passes through in 1 minute, so amount of time. So the equation to use is this here. So F equals delta mv over t. We're after the mass, so we're going to rearrange it. So we're going to put ft, then divide by the velocity is going to equal to the mass. So therefore, mass is going to be equal to 42,000 times by the velocity it's increased by. So 540, technically that should be there, sorry. So 540 and then times by, wait, I've gone wrong there, sorry. 42,000 times by the time. So time in seconds is 60, divide by the change of velocity, which is 540. So if you do all that into a calculator, we're going to get basically 4,666, etc., which is option D. This next question, the style catches people out quite a lot. Is after a wire that's being stretched, there's a really important word in here that catches people out. So uniform wire is stretched by a load F. The strain energy is E. The load increases from F to 2F, and it obeys Hooke's law. So when it obeys Hooke's law, that means K is constant. So spring constant is the same throughout. What is the increase in elastic strain energy stored in the wire? So what we have to do first of all is look at, so Hooke's law says F equals Kx, so that applies, and therefore we can work out the extension. Should use delta L, sorry, because that's what AQA uses, so delta L. So delta L is equal to F over K. Next, what we do is look at expressions for elastic strain energy. So we know that elastic strain energy is equal to half, and we know it's equal to, a couple of things, basically, but half F times by the extension. Now here, we can't use the extension because the extension is changing. So what we've got to have to do, because we just derived this term for extension, we know that the force doubles, so that's what we can look at, and we know that K is constant. So what we're actually going to do is to put that expression in here and say that the extension is now going to be F over K. Everything else stays the same, so strain energy is equal to half times by F. And obviously we can simplify this down. We've got two F's here, so half and then F squared over the spring constant. So the relationship we've sort of found is that because K is constant, that's why I've tried to put it in here instead of extension. We now just have two variables or two things that are changing. We have elastic strain energy and we have the force. And the relationship is that elastic strain energy is proportional to the force squared because that's constant and that's just a half. So when it says that F increases from F to 2F, what's happened here is that we've got an increase of times by 2, but it's 2 squared because it's in a bracket. So therefore, this goes up by a factor of 4. So here's the trick, okay? A lot of people just write down D, but the question says, what is the increase in elastic strain energy? So the increase, it goes from E to 4E. So therefore, the change that's happened there is actually 3E. So 4E minus E is equal to 3E. Okay, this question should be one of the quicker ones you can do on the paper, so see how quickly you can do it. Power is energy or work done divided by time. It's all about a spring which has a stiffness and is experiencing a force and extends by delta L. So the power is energy over time. The energy is going to be equal to half force times by extension all over time. So out of all the different options there, we haven't got F in it. I've done the wrong one. So you could also say energy is equal to half K times by delta L squared. So I'm going to change it into that because those are both equally valid equations. And then we just sort of see which one looks most similar to it. So it's option C here because we've got half on the bottom and L squared. Okay, this one is a little bit tricky. Electricity questions can be quite tricky. I'm going to draw it out. We've got a resistor connected to a circuit with EMF of 2 volts. It's got an internal resistance of 4 ohms, and then the big resistor, the load resistor in the circuit, is going to be equal to 12 ohms. Now, the question says, what is the PD across the resistor? So a lot of people, and myself included, spend a bit of time sort of struggling, like, oh, which of these versions of this equation do I use? Do I use this one? Do I use this one? You can't really use those because we don't know what the PD is when the current is flowing. We can't work out the current. You can't just do, 2 divided by 16 gives you the current, because like we don't know what with the value of the current flowing, we don't know what the EMF changes to, so we can't work out what the current is. Either way, you don't actually need to here. Effectively, even though this resistor is next to the cell, it's basically the same circuit as if we were to have just a 4 ohm resistor and a 12 ohm resistor. So basically, I've got 2 volts. I've got to split into this ratio. It's essentially a potential divider circuit. So potential difference across the resistor, meaning across the 12 ohm resistor, we've got a ratio of 1 to 3. So therefore, I've got to split 2 volts into a ratio of 1 to 3, which is going to be a ratio of 0.5 volts to 1.5 volts. We could use a potential divider equation if we wanted to, and the one across the 12 ohm resistor will equal 1.5. So it's option D. Simple harmonic motion and circular motion finally comes into our paper. We've got a circular motion, and this looks like complicated, but the question is honestly really, really straightforward. The mass remains at rest. What is the direction of the frictional force on the mass at the instant shown? So in questions like this on a horizontal turntable, the sort of objects, whatever they are going to be thrown outwards, and the friction is the force that's keeping them inwards. So the arrow is just pointing from P to O to keep them towards the center. So it's just going to be option A for that question. This type of question has come up several times on AQA papers. I think they get a bit lazy with these types of questions. The particle mass moves in a circle of radius r. Number of revolutions completed per second is F. What's the kinetic energy of the particle? So Ke equals half mv squared. We define an expression for V, all to do with its circular motion. So kinetic energy equals half m. And instead of V, we can say the V is going to be equal to, for a circle, 2 pi r over t. Now, t is the time period. We know we ask for answers in terms of f. So f is equal to 1 over t. So therefore, we can then equivalently say that equals to 2 pi r f. So that's what I'm going to put in here. So 2 pi r f all squared. Then basically, you're just expanding out and trying to simplify, although I don't think there's much you can do to necessarily simplify here. So half m, and then I've got 4 pi squared r squared f squared. The 4 and the 2 cancel. Don't cancel, sorry, but I've now got the half cancel. So now I've got 2m pi squared r squared f squared. Which one does this match up most closely with? That would be option B. On to question 30, and it's a fairly rare outing for our equation from our equation sheet, which is the one for speed in a simple harmonic motion, a system exhibiting simple harmonic motion. Usually we are used to work out the maximum speed. However, this is the original equation. It's given to you. A is amplitude, x is displacement. So it's equal to the positive or negative of the square root. I messed up this bit there. Positive or negative of omega, times by the square root of a squared minus x squared. So in the question, the amplitude is 0.6. The displacement x is 0.2. The time period is 2 pi seconds. So actually, the time period is 2 pi over t. However, the time period is 2 pi. So therefore, we can just say it's 2 pi over 2 pi, which obviously cancels, which is quite nice. Then we've got 0.6 squared minus 0.2 squared. And like I said, this bit cancels here. So all we've got to find out is the square root of that value, which if you put that into your calculator is square root of 0.32, which is 0.57. So option B. Okay, finishing up with 2 more simple harmonic motion questions. So mass m is suspended from a spring. It extends by distance x vertically and oscillates for time period t. M is removed and we have a different spring, so different k, and the spring extends by a distance of half what it was earlier. So we are then asked for what's a new time period of oscillations of m. So the equation we've got to use is this one here. So time period is equal to 2 pi m over k. So it's the same m, it's a different k. So the relationship between the two is going to be equal to t is proportional to 1 over k. So we don't have information about what this k is different by, but we do know the spring extends by a distance half of what it was earlier, and it is the same force. Yeah, it's the same mass, so therefore it's going to be the same force. So if we know F equals kx, basically if it's the same force, if x is going to be divided by 2, that means k has to be multiplied by 2, because those two things are inversely proportional if F is constant. So basically if I've got half the x, I've got double the k, so therefore I can put 2k into this thing here and then just find out what the relationship is. So if I know I've got different k, it's just looking at these and see which one matches up most closely. So I can, for those who don't know, I can rewrite this as saying 1 over root k. So therefore it's 1 over 2k because we got 2 in there, meaning that's going to be option B. Question 32 has come up quite a few times in AQA past papers. We've got a mass spring system and a simple pendulum with identical periods of oscillation. Both get taken to mysterious planet X, where the acceleration due to gravity is half. What are the periods of the mass spring system and the simple pendulum? Now, the mass spring system, as we just looked at, the equation is 2 pi big square root m over k. There is no value for g in here, so g does not affect it. So the time period is going to be exactly the same. Simple pendulum, on the other hand, we know is equal to 2 pi big square root L over g. So because g has gone down by a half, I've not got much room to do this down here, but g's gone down by a half. So therefore, basically, we've got t is proportional to 1 over root g, and then this has gone down by a half. So effectively, we can then say that's going to be equal to 1 over a half. So 1 over a half is going to be equal to basically proportional to root 2 instead. So therefore, it's option C. And that's the end of the paper. If you found that useful, please drop it a like. And if you want me to do more, definitely let me know in the comments. And I hope you found this useful. Check out my other A-level videos for more physics content. See you next time.